Okay, in this lesson we're going to be going over range, variance, and standard deviation. We're going to be doing this a little bit differently this time with the Excel sheet on the left-hand side and the PowerPoint on the right-hand side. We're going to be going through the lesson, doing both at the same time. So by the conclusion of this lesson, you're going to be able to know how to compute and interpret the range, variance, and standard deviation. Okay, so why should we study dispersion? The dispersion is a variation or spread outness, if you will, in a set of data. So there's three different ways that we can, or three different terms that you really need to know, which is range, variance, and standard deviation, that really describe spread outness. So the formula for range is range equals maximum value minus minimum value. And so over here on the left-hand side, we have the Excel book. We're going to be looking at some data that it's essentially the months of individuals keeping smartphones before upgrading. So we're going to be looking at the range, we're going to be looking at the variance and the standard deviation of all of this information. Recently a report came out that individuals are keeping their smartphones longer. So I was like, hey, let's take a look at this data. So let's first take a look at the minimum. So we're going to look at well, let's look at count equals count, and the formula count counts everything that is a number. So there are a total of 401 records or 401 observations that we're looking at. And now let's look at minimum. Minimum, let's look down here, equals minimum returns the lowest number. So there's one individual who only kept their smartphone for 0.73 months before upgrading. Then the next person equals max. Then this is the longest that anyone in this particular sample kept their smartphone before upgrading, which is 39.48 months, which sounds a lot like me. And so that's the minimum and the maximum. And now we're going to look at mean. The way that we do mean is we do equals sum divided by count, which gives us a mean of 20.55. So the average individual in this sample keeps their phone for 20.55 months. So the range is the max minus the min, so the highest number in this observation, or in this set of observations, and you subtract the smallest number in this set of observations. So we're doing equals max minus min, and that gives us a range of 38.75 months. Okay, so and that's max minus min. So what we're going to be doing now is we're going to be looking at the variance. And you can see all the way down here, this is all the different observations. And we're going to do, let's see here, outside border, just so you can kind of keep track there. In order to do the variance, it's kind of like a three-step process. And let's see here, population variance, and we're going to go with, well, we'll do population variance first, and then we'll do sample variance second, and I'll tell you what the difference is between those in just a minute. Okay, so x minus x bar, so we do equals the observation, x, minus x bar, which is the mean, except we're going to put a fun little dollar sign right here because when you do the dollar sign, what it does is it makes it so when you drag it down, the 7 never changes, so it always goes to the b, or to the mean. So we're going to drag it all the way down, and that gives us x minus x bar, And I'm going to show you what happens if you add all of these up. It adds to 0. And the reason why it adds to 0 is this is essentially measuring each individual observation's distance from the mean. There are some that are below the mean, some that are above the mean, and so if you add up all of these, it should equal 0 because the mean is the average of all of them, therefore it should equal 0. So that doesn't really help us all too much. But what will help us is we need to square these observations, or square these distances from the mean. And we're going to make this we'll go with 3. And we're going to bring this down. And so this right here is the individual squared distance from the mean, which when you square it, what it does is it makes it so that when you square it, it makes it so that nothing is negative. So now what we're going to do is we are going to sum all of these, and you'll see that number is a lot greater than 0. And then to finally, so you're adding up all of the observations squared distances from 0, or sorry, from the mean. And now what we're going to do is we are going to do equals this, the sum of all of those divided by the total number of observations, which is 40.16267, and that right there is the population variance. Okay. Now the let's do this. Okay, the population variance. Now we're going to do something called the sample variance, which is slightly different, but it's not going to change all too much. Okay, so we've got this right here, which is the sum of all of the squared distances from the mean. So equals divided by the total number of observations minus 1. Okay, and the reason why we do this, you see, it doesn't change all too much, but the sample variance basically accounts for there's a likelihood that there may be more variation in the population than in the sample, so it's better to be a little bit more cautionary when utilizing a sample variance as compared to a population variance. A population variance, you know all the parameters of the population, where with a sample variance, you don't really know all the parameters of the population. You're just pulling a sample out. Okay, and so we intentionally do n minus 1 in order to allow for that the possibility of having more variance and just being a little bit more conservative in our interpretation. Now, looking at the population variance, the equation over here, you have the lowercase sigma squared. It's referred to as sigma squared, or the population variance, equals uppercase sigma, which is you sum x, or the observation, minus the population mean, and you square that. And so you're summing that, and then you're dividing it by the total number of observations in the population. Okay? And then the sample variance, like I said, is almost the exact same thing. but it's the number of observations in the sample minus 1, which allows us to be more conservative in our interpretation and just provides for more reliability. Okay, so example sample variance. We just did this, and I just showed this to you over here, but here's another example. An hourly wage for a sample of 5 part-time employees at Home Depot are $12, $20, $16, $18, and $19. The sample mean is 17, so what is the sample variance? So you take 12, 20, 16, 18, and 19, and you subtract the mean from that. So $12 is $5 less than the mean, $20 is $3 more than the mean, 16 is $1 less than the mean, 18 is $1 more, and 19 is $2 more. And then you square that, which gives you 25, 9, 1, 1, and 4. You add that together, and that gives you 40. So this is just a sample of them, and so you do 40 divided by n minus 1, which gives you this sample variance, which is $10 in squared metrics. So that is the sample variance, but sample variance really doesn't do too much for you, and the reason why is because it's the squared unit. What we want is the actual unit. Okay, so that's what the sample standard deviation is. The standard deviation literally means this is the average amount that an observation deviates from the mean. Okay, the average amount that an observation deviates from the mean. So we've got the standard deviation is the variance. Here, let's do this. Insert sample standard deviation and then population. Okay. So equals square root of the sample variance, and then this is equals square root population variance. Okay, and you'll notice that the sample standard deviation is actually greater than the population standard deviation, which just helps us to be a little bit more conservative in our interpretation. And so we took a square root, and now that we took a square root, we are able to utilize that information in interpreting our data. So what does this actually do for us? So what is a standard deviation? The major characteristics of the standard deviation are that it's in the same unit as the original data. It's useful, it's meaningful. That 6.3374, it means that on average, individuals keep their phones for 20.55 months. But the population standard deviation says that deviates by 6.3374, which is a pretty large standard deviation for that mean. So 6.3374, that means that within one standard deviation, so let's take a look at this. 20.55 is the mean. Okay, so we have equals sum, comma. Okay, so 26.88 or equals minus. That is one standard deviation, 14.21 months to 26.88 months is within one standard deviation of how long people keep their phones. But what does that mean? Okay. That means that 68% in a normal distribution keep their phones between 14.21 months to 26.88 months, which that's really great information. Now, if you wanted to increase that, okay, so equals minus, okay, equals plus, okay. So a total, or 95% of people keep their phones between 7.875 months and 33.224 months. So this is a really great tool that helps us to interpret normal distributions. So if you know that you have a normal distribution, which we're going to talk about that a little bit more later, but if you know that you have a normal distribution, you can apply these rules very easily. Going back, I kind of skipped over something a little bit earlier. Standard deviations cannot be negative. They cannot be negative. And then also, it's the most widely used measure of dispersion. So if you're going to use something, use standard deviation. Very few people use variance. Range isn't used nearly as much, but the standard deviation is used throughout almost everything that we do. Okay. And if you want to add one more, hold on. Control X. Let's do this. Equals minus equals plus. Okay, so 99.7% of individuals keep their phones between 1.53 or 1.54 and 39.56 months, which that's what this says right here. Okay, so that's where we're going to end for this lecture, because the next lecture, is a little bit much for this.